Hey everybody, it's Friday, April 9th, and as you can see here in the aim today, our goal for today's video is all about how we can use concepts associated with energy and simple harmonic motion to describe the motion of a pendulum. In the simple harmonic motion unit, we basically have two phases, the simple harmonic motion of a spring block oscillator and the simple harmonic motion of a pendulum. And the pendulum piece is the last piece of this unit, and because this is the last unit of the course, this is really the last piece of new information that we have to discuss for the entire course. We have finally made it. Having said that, though, before we jump into the simple harmonic motion of a pendulum, which really is going to be the focus of the vast majority of this video, I want to take a brief moment to just jump back into the spring block oscillator for a second. And the reason why I want to do this is because there is sort of an abstract concept that we have been dancing around for the entire year that sometimes on the AP test they ask multiple choice questions about, but it's also one of those questions that they say can be an experimental design question. And they've never asked this question as an experimental design question on a practice test or on the actual AP test. And so it stands to reason this is coming sometime, and it very well could be this year. And if that's the case, I want to make sure we take a moment to sort of remind you about what we said about this concept and sort of talk about its applicability to the simple harmonic motion of a spring block oscillator. And so if you remember back when we were talking about gravity, we were talking about the difference between inertial mass and gravitational mass. Now, this is one of those weird topics, as I said when we were first going over this, because it seems like it's a meaningless distinction. You don't really need to go too nuts about the difference between inertial mass and gravitational mass because there is no difference between inertial mass and gravitational mass. They are the same thing. The reason why the people who designed this course like to include this in this course is because physicists did not know that inertial mass was the same thing as gravitational mass for a long time. Part of what the AP course description says is you should be able to design an experiment in which you detail the difference, detail an experimental method to determine the difference between the inertial mass and the gravitational mass. Now, obviously, the result of that experiment is going to be that there is no difference, but let's just go ahead and tie all this together and wrap this up. As a general reminder, gravitational mass is mass as a measurement of how an object interacts with a gravitational field. In other words, it's the mass as used in the equation Fg equals mg. It describes how an object interacts gravitationally. That's the basic idea. Now, as we know, mass is mass is mass, but they didn't know that. They thought that the way that an object interacts with a gravitational field is different than the way an object interacts with any other force. Anyway, to determine mass as it measures how an object interacts with the gravitational field, we want to think of how we can measure the mass as being moved solely by gravity. And the obviously easiest way to do that is by using any method involving the force of gravity, like, for example, using a triple beam balance. It's important to realize in the context of these experiments, if you are just popping an object on a triple beam balance, because it is gravity that pushes the object down into the balance, what you're doing is you're measuring the gravitational mass. That's the first piece. Now, of course, they are going to want you to compare the gravitational mass to the inertial mass in these kinds of questions. And so it's important to realize that inertial mass is essentially the concept of mass being a measurement of inertia. In other words, how difficult it is to accelerate the object due to any ordinary force. And so in other words, this is the mass as used in the equation F net equals ma. Again, obviously, as far as you know, the mass in the Fg equals mg equation is the same thing as the F net equals ma mass, but the experiment, at least as far as the course description is concerned, wants you to be able to prove that. So the question is, how are you going to be able to design an experiment to determine the inertial mass? If I asked you measure the mass of an object, you'd probably put it on a triple beam balance. But of course, there are other ways. We actually did already this year talk about an experiment where we could use a tabletop Atwood's machine to measure the mass of an object. An Atwood's machine, because the object is being accelerated by a tension, and so F net equals ma is obviously the governing equation, is going to be a really important way to do that. The main reason why we are talking about this today is because in addition to an Atwood's machine, being a good method for you to be able to do that, it's important to realize that a horizontal spring block oscillator is also a great way to do that, because the inertial mass can be measured using any method that does not involve gravity. And so the basic idea here, I think, is pretty straightforward. If we take a block on a frictionless surface and we attach it to a spring, then we can use the information about its oscillation to determine the mass. That really is the point of this experiment and the reason why we are discussing this at this juncture. If you use a horizontal spring block oscillator, you can measure the mass of the object essentially by determining the period of the oscillation and the spring constant. If we know the spring constant, we can measure the period to determine the mass. That's the point of this discussion. If we have a frictionless surface, and I guess I'll just go over here and write, this is a frictionless surface, then this will be a perfectly reasonable way for us to measure the mass. Now, I'm sure some of you might be thinking, well, isn't there really no such thing as a frictionless surface? Sure, that's true. But it's important to realize in the lab, we have carts that go on a track that is generally referred to as a low friction track, because it is definitely true that it's not a frictionless surface. It's pretty close. It's also important to realize that super tiny amount of friction is not going to mess with things anyway, because even though there is a super tiny amount of friction, meaning technically it is a damped oscillator or an oscillator that is experiencing damping, the damping doesn't affect the period. As we said yesterday, the only thing it affects is the amplitude. And so just as long as we are measuring the period before the thing like really slows down to a stop, we're good anyway. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, of course, a pretty reasonable question would be like, well, isn't that kind of an insane way to measure the mass of an object? Shouldn't we just throw it on a triple beam balance? Isn't that the easiest way to measure the mass of an object? Of course it is. But should you be presented with a question on the AP exam about the difference between inertial mass and gravitational mass, what I have been trying to train you to say the whole year was that an Atwood's machine is a good way to get the inertial mass and a triple beam balance is a good way to get the gravitational mass. It's important to realize a spring block oscillator is also an excellent way of determining the mass of an object. While we're on the subject, just very briefly before we move on, I think it's also important to recognize, yeah, we can throw an object on a scale to measure its mass, but of course that only works in a situation where there is a gravitational force that is capable of being canceled out by a normal force. If the object is in free fall or in orbit, then we cannot use that idea to measure the mass of an object. This is actually a pretty significant problem for astronauts on the International Space Station. They do not just stand on a scale to measure their mass because there is no normal force to cancel out their gravitational force because they're in free fall. How do they get around this problem, you ask? They use a spring block oscillator, essentially. They experience simple harmonic motion when they sit on this little spring here that's inside of the housing of this machine. They oscillate. The electronics in the machine determine the period of the oscillation, of course, with a known spring constant, and they use that to determine their mass. This device is called a body mass measuring device, or a BMMD. And if you Google that, you will be able to see a video that goes into how this device works in more detail. The basic idea is that they just use the period of the oscillation to determine the mass of the object, because the oscillation of this person, in terms of its period of the oscillation in relation to the person's mass, is a pretty well-defined thing. And I like this because I think that's a pretty cool practical application of the physics we learned in this class. And with that, that brings us to the main topic for today, which is the simple harmonic motion of a pendulum. A pendulum, as far as we've said so far, is a device that swings back and forth. That should give you a pretty good idea of why this thing is experiencing simple harmonic motion. It is an object that swings back and forth between two extremes, and it does that under the influence of a restoring force, which is always trying to return it to its equilibrium position, which, as I hope you can tell just from thinking about it, is basically here, because the thing would just be hanging straight down. I like this image here because it also shows you that if you actually attached a pen to the bottom of the pendulum bob, remember the bob is the name we give for the ball at the bottom of the pendulum, If we attach a pen to the bottom of this thing and have it like trace over a piece of paper, it will actually trace out a sinusoidal curve as it swings back and forth. A pendulum, because it is involving motion back and forth between two extremes and traces out a sinusoidal path that is something that experiences sinusoidal oscillations, is an excellent example of simple harmonic motion. And as a result, it is something we talk about in this course. Now, depending on how much time we have in this course, sometimes I show the derivation for the period of a pendulum equation, sometimes I don't. I think what I'm going to sort of do is take the in-between path in this instance and sort of go through the derivation very quickly, but not show the entire thing. The reason I want to do this is because I know some of you have aspirations to go to school for science and engineering, and the basic like trick or shortcut that is used in this derivation is definitely something that you're going to see when you go to upper levels of science and engineering education. And so that's something I'd like to go through now. Let's take a moment to look at how you can derive the equation for the period of a pendulum experiencing simple harmonic motion. Here is a basic free body diagram, obviously not an official one because it has components in it, but a basic free body diagram of the pendulum. Now, as it turns out, this angle, the angle to which the pendulum is being raised, is equal to this angle down here. They're essentially similar triangles. Well, I guess this will only take a second. If you don't see it, it's because we have alternate interiors. So there's our first Z. So that tells me that this angle right here is equal to this angle right here. But notice this angle right here is not the angle in the triangle. But of course, we have another alternate interior Z there to there. I'm going to extend that one just so you can see that line to there, and then up to here, which shows that that angle in the little triangle is going to be equal to that angle being traced out by the pendulum. Okay, so we can look at this force, which is trying to restore the object back to the equilibrium position, as being a component of the gravitational force, which is parallel to the motion. Notice this thing is always going to act toward the equilibrium position, so that when the pendulum bob is on this side, it's going to point back down to the bottom, and when the pendulum bob is on this side, it's going to point back down to the bottom that way. That's just how gravity works. It always brings things down. And because this perpendicular component here is actually this part of the triangle, it's opposite of that angle, the vertical angle. Remember, there's like an inclined plane, so the sine and cosine switch. And so it will be described by a sine function. And so the component of the gravitational force, which is acting as the restoring force here, is the component of the gravitational force, which is parallel to the pendulum's displacement. Okay. So what we are saying here is that the restoring force is equal to negative mg sine theta. Again, negative because it's acting, as you can see over here, down. Now, the concept that comes up in your future science and engineering coursework, should you decide to take that path, is a concept called the small angle approximation. And what the small angle approximation says is that for small, super small angles in radians, the sine of the angle is actually approximately equal to the angle itself. So in radians, the sine of the angle is approximately equal to the angle. And what I'd like you to do here is just pause this video for a second and test this out in your calculator. I'll just give you a few examples. The sine of 0.05 is 0.04997917. Very close. The sine of 0.1 is 0.0998. And so it's close, but it's not perfect. This is called the small angle approximation. And so what we're essentially going to do is we're going to replace sine theta in this equation. Instead of having negative mg sine theta, we are going to have negative mg theta, because the sine of the angle in radians, when the angle is tiny, is approximately equal to the angle theta. Now, some of you might be thinking, well, why the hell are we doing this with such small angles? Because is that really going to matter if these angles have to be so small? Let's not forget that 360 degrees is only like 6 and change radians. So like 0.2 as the example that I gave for radians is about 11 or 12 degrees, somewhere in that range. So we'll go back and address that in a moment, but you can see it's actually for like a reasonable number of degrees that this works. Okay, now why are we doing this? Because now we can use the sides of this triangle, which notice we are cheating a little bit here because this is not actually flat, this displacement part for the pendulum, because it's not going in a straight line, it's tracing out an arc at the bottom, as we could actually see in that little PowerPoint slide. It's tracing out an arc right here, but it's close enough, again, and if it's a small angle, it'll basically be straight over those super small angles, just kind of like how the Earth is round, obviously round, but the when you look at it over a small enough section, it looks flat. And so we're basically now able to write an equation for the angle in terms of the length of the string, L, and the basically like the height that this thing is traveling through. Again, we're calling it y as a height because that distance it travels, that flat part of the triangle, is a height, or at least is like a component of the height. And when we do that, we can sort of rewrite the equation negative mg sine theta as approximately equal to mg theta, and using sine opposite y over hypotenuse L, we can rewrite that equation as mg y over L. And now there should be negative signs here. You would never ordinarily see this in class. These are from my own notes. I dropped the negative. There should be a negative there. Okay, so the key thing to notice about this equation is that this one doesn't work for us because restoring forces, which are always opposite of the displacement, that's why it has a negative sign, also have to be proportional to the displacement in order for this to qualify as simple harmonic motion. If you forgot that, if you go back in your notes or you go back to that video where I first introduced simple harmonic motion, I said simple harmonic motion is only technically simple harmonic motion if the restoring force wants to restore the object to equilibrium and it is proportional to the displacement. Now that we've used the small angle approximation, the force is directly proportional to the displacement. And so what I've written here is, notice this equation now has the form, or now takes the form, of F equals negative kx. Now this part is a little sketchy, but the spring force equation is proportional to the displacement times some other constant. And what you notice when you look at this equation is that m, g, and L are all constants. The length of the string is not going to change. The mass of the thing at the bottom is not going to change. And G on the surface of the Earth is not going to change. So effectively, it kind of takes the form F equals negative kx. And so instead of writing that as F equals negative kx, we're going to write it as F equals negative, our constant here, mg over L, times the displacement y. Now, this is going to seem super sketchy to the point where you're almost going to think it's ridiculous. But I think what's cool about this is it actually works. All of this is built on like what seems like a house of cards of assumptions, and yet it still works. Believe it or not, what we actually do now is we say, well, the spring constant k, we can sort of say this thing is functioning as, this mg over L term is kind of like k because it's a constant. The spring constant k is in the period equation for a spring. And so if this k term is basically functioning exactly like k in the spring constant equation does, because it's constant, then we can just go to the period equation for a spring, replace mg over L for k, and see what we get. And when we do that, that equation says t equals 2 pi m over k. We plug in for k mg over L. What we end up getting once we flip and multiply, recognizing that we're dividing by a fraction, we get ml over mg, and that leaves us the final form of the equation. The period of a pendulum is 2 pi times the square root of L over g. All right, now let's just go through very quickly and define our terms here. Of course, the symbol for the period of a pendulum as shown in the AP Physics reference table is T with a subscript P. The equation, as we just saw in the derivation here, is that the period of a pendulum is equal to 2 pi times the square root of L over G, where, of course, L is the length of the pendulum string, G is the gravitational acceleration on the surface of whatever planet that pendulum happens to be located, and T with the subscript P is the period of a pendulum, of course, measured in seconds. Notice, of course, the argument of that square root, meters divided by meters per second squared, ends up giving you units of seconds squared, which, when you take the square root of that, ends up giving you units of seconds. And, of course, the unit for the period of a pendulum is in seconds. Now, it should be noted, you can go and confirm this by looking yourself, the period of a pendulum equation is the only equation about a pendulum in the AP Physics reference table. Of course, the frequency of a pendulum's oscillation could be an important measurement as well, and so it's probably just important for us to note. In exactly the same way, we said you can take the period of a spring and flip it over. Due to the inverse relationship between the frequency and the period, you can do the exact same thing with the period of a pendulum equation to get the frequency of a pendulum. You take the inverse of the 2 pi, so we get 1 over 2 pi, and then we take the inverse of that square root here to get square root of G over L. Of course, the terms all mean the same thing. We can add down here, though, if you want, that F is equal to the frequency of a pendulum measured in hertz, and there we have it. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so just very quickly before we move on, I think it's important to just take a moment to really look at this equation and try to understand exactly, first of all, what it says and perhaps what it doesn't say. And so the first thing we should look at here, and I guess you could write this under the heading Notes on the Period of a Pendulum equation. The first thing we should say is the period of a pendulum is directly proportional to the square root of the length of the pendulum string. That we can very clearly see in the equation. The period of a pendulum is directly proportional to the square root of L. Now, I think that makes a pretty good amount of sense, but only if you recognize the structure of the restoring force. I think the key detail here is really understanding that the way the period of a pendulum is affected is by changing the magnitude of the restoring force, because the restoring force here is gravity, or at least the component of the gravitational force that's parallel to the path taken by the pendulum. So the first thing that we should say then is, if you look at the structure of the restoring force, that equation, we have negative mgy over L. And so basically what we're saying then is the restoring force, I'll just write F restore here, is inversely proportional to the length. And so hopefully by realizing that, you can sort of see the logic a little bit here. A larger length effectively means a smaller restoring force parallel to the displacement. The idea is the longer and longer you make the length, the less and less parallel the force becomes, or the actual force of gravity becomes to the path, and so you get a smaller component, basically. And a smaller restoring force in the direction of the displacement means the thing is going to accelerate less in the direction of the displacement. And if that's the case, then it does make sense that it is going to take a longer time. We should also probably say, just while we're on the subject here, that the period of the pendulum is inversely proportional to the square root of G. That should also make sense, because if we were on a planet with a slightly larger gravitational acceleration, or if we could just like turn a knob and increase the gravitational acceleration on the surface of the Earth, now you're going to have a bigger force accelerating the pendulum, trying to bring it back to its equilibrium position. And so it makes sense then that that would decrease the period. What we should also say, just very quickly then before we move on to solve some problems, is the mass of a pendulum bob has no effect on the period of the pendulum. Notice it's not in the equation. This, I think, makes a really good amount of sense if you take 1 second to think about it. The restoring force in the case of a pendulum experiencing simple harmonic motion is gravity. So essentially what we're saying is here, the mass of an object isn't going to affect what gravity does to it. And like, duh, we've been talking about that forever. Right? It has more inertia if it has more mass, which means it's harder to move. Yeah, there's more gravitational force acting on it, but it has more inertia. Those two things effectively cancel, like it always does whenever gravity is involved. What we should also say is, notice, as is not present in the equation, the amplitude of the oscillation has no effect on the pendulum's period. And I just wrote pendulum here, so I should probably write pendulum's period just to finish that up, because, you know, that's a really similar idea to what's going on with the spring. You have this issue where you have, yes, maybe a different size restoring force acting on the thing when it's got to be raised to a different amplitude, but the point is it's got to travel more distance too. And so it ends up canceling. The basic idea here is that as you increase the angle, you have a larger component of the gravitational force that's acting in the direction of its displacement. That is true, but the displacement is bigger, so it has no overall effect. Take a second to pause this video here and write that down. And when you hit play, we'll move on. I want to take a second to just talk about that length issue, because I'm sure that some of you who are actively thinking about this are thinking, well, if you have a longer pendulum and a shorter pendulum and you raise them to the same angle, well, isn't the longer pendulum just traveling a larger distance? And so isn't that really kind of like the amplitude? It's not really like the amplitude, because the amplitude is all about the angle in this case, really. But it all comes back to the restoring force and the way the angle and the height and the length are related. The basic idea is that the restoring force is inversely proportional to the length. And so when you increase the length of a pendulum, you actually decrease the restoring force, you know, that component of the gravity that's acting parallel. And so that ultimately is why it takes a longer amount of time to swing back and forth. Now, I would imagine that you will have some sort of intuitive understanding of this after, you know, playing around with it and having done some experiments. But obviously, since we are not in school, we can't actually do this experiment. Having said that, let's be totally clear, it is absolutely experimentally confirmed that the period of a pendulum is directly proportional to the square root of its length. A longer pendulum has a smaller restoring force acting on it. If it's easy to think about, the fact that it's longer means at the same angle, it has to travel a longer arc length than a shorter pendulum. That works, at least for a mental model, but just know that it's slightly off. What I want to show you now is a video, essentially a video of this experiment showing the relationship between the period of a pendulum and its length, and showing how it's not affected by the amplitude or not affected by the mass. Okay, so in this video we have this famous professor over here, Walter Lewin. He was a professor at MIT for a long time. Some of you might have seen his videos online. I think I've showed a few videos. I forget what topic it's on right now, but in the honors class. And he's going to demonstrate here first, at least, that the period of a pendulum is not dependent on its amplitude. So he's telling kids right now, he's got this mark on the floor right here, that's 5 degrees. He's got this mark over here, that's the 10-degree mark. And when he's going to hold the pendulum at those 5-degree and 10-degree amplitudes, if you plug the length of the pendulum, which is 5.21 meters, and g, 9.8 meters per second, into the period of a pendulum equation, you're going to get that the period is going to be 4.58 seconds plus or minus 0.02 due to experimental uncertainty, the measurement of the length, et cetera, et cetera. Now, he also explained how he's going to measure 10 periods, and so we'll pick it up from there.
Degrees, this is 5 degrees, and when I hold the ball here, it's 10. Timing is not easy. The best way to do it is to start the timing when the pendulum comes to a stop. That is rather well defined. And then you let it swing 10 times, and then when it comes to a stop, you stop it. And it would help me if you would count how many oscillations we have made. Because then I don't have to look at it. All I have to do is when I come close to 10, I have to watch for the moment of stopping, and then I will have it. So, we'll do this first at 5 degrees. I'm going to start it when it comes here. Yeah. Okay, now you count.
Speed this up a little bit.
You're doing very well. You're going to pass this voice.
All right, so the period of the pendulum there of 10 periods was 45.71 seconds. And so that means one period, because that was 10 oscillations, would be 4.57 seconds, which was well within the range of his prediction. So now he's going to do it again. He holds it at 10. And I'm just going to skip through this because you can imagine how this is going to go. 4.58 seconds, well within the range of experimental uncertainty. Now, again, this video is from something on YouTube called Walter Lewin for the Love of Physics. That was the name of the book he wrote. Good book, by the way. I would recommend reading it if I were you. It's pretty cool. From this little demonstration, he's shown the period of the pendulum is independent of the amplitude, which is the angle at which it swings out. You get 4.57 when you had it at 5 degrees and 4.58. But of course, because there's an experimental uncertainty with the reaction time, that's well within the range of experimental uncertainty. Okay, so we'll pick it right back up here. I don't think there's really anything that needs to be said. Just watch.
Now comes the hardest part. The hardest part is that we have to change the mass of this object. And the way that I'm going to do that is prominently demonstrated on the cover of my book. Yes, I'm going to hang on that pendulum. It is a difficult demonstration. First of all, it is painful. It really is. Second, the timing is tricky. Because when you look at a pendulum and when you see it stand still, that's really well defined, plus or minus 0.1 second. When you are swinging yourself, however, then you can only do it by sensing the moment that you think you stand still. And that's what I will do. And then you will do the counting. And this is very unpleasant. It is. Oh, there's something else I haven't told you. If you're a good physicist, you will say, if you're going to sit on that ball, then effectively you bring the mass of the ball up, and so the length of the pendulum will shorten, and so you get a shorter period. And I know that too. Therefore, I will have to stretch my body so that when it is here, that it is almost completely parallel to the floor. If I don't do that, I will not be able to convince you that the period is independent of mass. And that makes it very difficult. So I will start it at some moment, you will see when, and then you do the counting.
All right, I'm going to skip forward here because they mess it up first.
Nobody knows why. Ready?
Here we go.
Oh, this really hurts. Can't you count a little faster?
And there we have it. 4.58 seconds. Period of a pendulum is independent of its amplitude. It's independent of the mass. And we can confirm that experimentally. All right, now just very quickly before we solve a problem, I want to just go ahead and show you this graph here. As you can see from this graph, this thing is trying to show you a comparison of x, which in this case is the angle theta, the sine of that angle, and the tangent of that angle. Notice here, this angle on the x-axis here is being measured in radians, and on the y-axis they're showing the value of the function. The whole point of this graph is so you can compare the angle to the sine of the angle to see how well the small angle approximation works. Now, generally what we're going to say is if the angle is less than about 15 degrees, then the small angle approximation is going to work excellently. We can see how that justification could be made based on what this graph shows. Notice here at 0.2 degrees, it's basically impossible to distinguish between these two lines, to distinguish between the red line and the green line. Remember, the red line is showing you the angle theta here. The green line is showing you the sine of the angle. So at 0.2 radians, it's basically impossible to distinguish the difference on this graph, at least between the angle and the sine of the angle. Now, 0.2 radians is about 11.5 degrees. Notice, even at 0.4 radians, these lines are very, very close to overlapping. They're barely different from each other. And 0.4 radians is about 23 degrees. And so notice here, we're going to just, for safety, say Any angle that's below 15 degrees, this small angle approximation is going to work really, really well for, and so that's what we're going to keep it to. You'll notice here, obviously, as the angle continues to deviate, to these larger and larger values, you get some separation between the angle and the sine of the angle, and so this thus is called an approximation. It's close enough at low angles, it kind of breaks down at larger angles, but for our purposes in this class, it'll be good enough. You'll notice when we take a look at problems, they will specifically say the angle is relatively small, and so you'll be able to know that the small angle approximation applies. Speaking of which, let's take a look at a problem. This problem here says the length of a simple pendulum is 0.760 meters. The pendulum bob has a mass of 365 grams, and it is released at an angle of 12 degrees to the vertical. Notice here they're telling us it's 12 degrees because they're saying, hey, the small angle approximation works here. Part A says, with what frequency does it vibrate? Assume simple harmonic motion. Again, that's kind of extraneous, again, because they already told us the angle's small enough that simple harmonic motion applies, but they're giving us an obvious hint here. B is asking, what is the pendulum bob's speed when it passes through the lowest point of the swing? And C is asking, what is the total energy stored in this oscillation, assuming no losses? All right, let's go take a look. Now, notice here, part A is asking us, what is the frequency? And so, as we already discussed, we're going to need G, which of course is reasonable to assume this thing is on the Earth here, and we're going to need the length of the pendulum. Now, notice here at the very beginning, they tell us the length of the pendulum is 76 centimeters. So we'll say here for part A, L equals 0.760 meters. We obviously know G, this thing is on the Earth, is 9.8 meters per second squared. We're going to always assume these things are on the Earth, and unless they tell us otherwise. And now notice here, I just got into the habit of writing T for the period of the pendulum, but of course that's not what they asked us for. They asked us for the frequency, and so we're going to go ahead and find the frequency of the pendulum, basically just by manipulating that equation for the period from the reference table. So if you look in your reference table, you will see the period of a pendulum equation is 2 pi times the square root of L over G. And so since we know the frequency is the inverse of the period, we're just going to flip everything over. 2 pi flipped is 1 over 2 pi. Root L over G flipped is root G over L. And so now we're in business. We can plug this thing in. We have the frequency is 1 over 2 pi times the square root of G, 9.8 meters per second squared, over L, which is 0.760 meters. And when you plug in those numbers, doing that math, making sure you're taking the square root, that's probably the most likely mistake you can make for this one, you end up with a frequency of 0.572 hertz. Now, of course, in a lot of situations, the period is going to be a measurement you want to know, particularly because period is something you can super easily measure, just like with a stopwatch. And just so we're being clear about it here, if we wanted to find the period just for fun, we could say here that the period is the inverse of the frequency of the pendulum here. And so that means if we plug that in, I guess I'll just do this quickly over here. That's 1 over 0.572 hertz. And when you do that math, you end up getting that the period is about 1.75 seconds. And that's it for part A. Now, it's important to realize that's really it for the simple harmonic motion part of this calculation. I've not really seen them ask a question where they ask you for the period or frequency and then transition it to an energy analysis. Because conservation of energy is such an important topic on the AP test, I figure we might as well take a look at this problem because it has some good energy stuff in it as well. Part B says, what is the pendulum bob's speed when it passes through the lowest point of the swing? So let's go ahead and do part B here. Now we're trying to find the max speed, V max. And so it should be clear to you here that the length of the pendulum bob is going to end up being something that's important. So that's 0.760 meters. As it turns out, if you remember this, the angle, 12 degrees, is also important. And we could write down the mass here. You should know what's going to happen to the mass. Remember, they said that was 365 grams, so we'll call that 0.365 kilograms. And we're looking for our Vmax, as we said. It's important to realize how obviously the pendulum is a conservation of energy problem. Pendulum converts gravitational potential energy when it's at the amplitudes to kinetic energy when it's at its equilibrium position. And so if we just sketch that out real fast here, when it's down here, it has all kinetic energy. When it was up here, it has all gravitational potential energy. And so there's a prime example of energy conservation. So we start by writing out here mg delta y is equal to 1/2 m Vmax squared. Now, of course, as is always the case with potential to kinetic energy transformations, the mass is going to cancel. And so we end up with a very familiar equation. V equals the square root of 2g delta y, or V max is equal to the square root of 2g delta y. Now, of course, the problem with this is we don't have the height. This is something that's really important to remember for the AP test in case it comes up. You can always use the length and the angle of a pendulum to determine the height. Now, notice here, this measurement, as I have it drawn in this system here, is L. Obviously, the string's not going to change when I pull it back, so this measurement is L also. And so if you look, this angle here that's given to us as 12 degrees can be related to this part of the triangle. And then this measurement here, from that dotted line down to where the pendulum bob was at its original position, is the height. Now, if you look at this part of the diagram, which I guess I'll blow up here just for the purposes of our discussion, this is our angle here, this is the length, and this is the side we're really interested in. Because this side of the triangle is the side adjacent to the angle, that's going to be L cosine theta. So basically what we're saying is that this length here, this whole length, is this part of the triangle, which we just said was L cosine theta, plus the height. That part of the triangle, L cosine theta, plus this part of the triangle, the height, equals to that whole thing, L. And so that means if we solve this for the height, we get L minus L cosine theta. And so that's what we're going to plug in. V max is equal to the square root of 2 times G times L minus L cosine theta. And now we're in business to go ahead and solve for this thing. V max is equal to the square root of 2 times 9.8 meters per second squared times the length, 0.760 meters, minus the length, 0.760 meters, times the cosine of the angle here, which is 12 degrees. So we have the cosine of 12 degrees. Now let me just sort of put a line here to get that off to the side. This is a little messy here. I apologize for that. The square root symbol is looking messed up. But when you do that math, making sure you're being really deliberate about these parentheses here for the L minus L cosine theta part, multiplying by 9.8, multiplying by 2, and then taking the square root, you end up with a maximum speed of 0.571 meters per second. And that's it. This L minus L cosine theta part is really, really important for determining the height of a pendulum. And it is something that I've seen come up on AP questions from time to time. So it's good to be able to recognize that and do that. Take a second to pause this video here and write that down. And when you hit play, we'll move on to part C of this question. All right, just very quickly here for part C now, I'll go back to the original question. They're asking us, what is the total energy stored in this oscillation? And I'm just going to zip through this because this should be child's play to all of you by now. We're looking here for the total energy after we just figured out what the maximum speed is. That means the total energy is just going to be equal to the kinetic energy associated with that maximum speed. So that's just going to be 1/2 V max squared. And so that means the total energy is going to be 1/2 of the mass, 0.365 kilograms, times V max, that maximum speed we just calculated, 0.571 meters per second, whole thing squared. And when you do that math, making sure you have those numbers plugged in properly, you get 0.0595 joules, which we can say, because that number is ugly looking, 5.95 times 10 to the negative 2 joules. It's a pretty light pendulum bob, and it's not raised to that big of a height. And so it starts out with a pretty little amount of gravitational potential energy. And that's why I think it makes pretty good sense that it's going to end up with a little amount of kinetic energy. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now very quickly before we get to wrapping this up here, I think I want to take a moment to just point out the large number of similarities that exist between the pendulum's simple harmonic motion and the simple harmonic motion of a spring block oscillator. Notice when these objects are at their amplitudes, they have no velocity. That's when they have their maximum acceleration, no kinetic energy, and all potential. And then we continue to see that cycling back and forth of potential and kinetic energy when they transition from amplitude to equilibrium position back to amplitude. These patterns hold, and I think that's the important point. When it's at the equilibrium position, it's got its maximum velocity, no acceleration, all kinetic, no potential, and so on and so forth. Notice here in this graphic, they're using 1/2 Ka squared as the representation of the total energy. Now, of course, the only difference between the pendulum and the spring block oscillator is that when the pendulum is at its amplitudes, the potential energy that it has is not elastic potential energy, but rather is gravitational potential energy. I think that makes pretty good sense. Also, when we were talking about the spring block oscillator, we took a look at a graph of the kinetic energy and the potential energy, and it should come as no surprise to anybody that this graph for a pendulum's energy when it's experiencing simple harmonic motion looks exactly the same. Here, it's important to realize displacement being 0 in the middle here tells you that that's the equilibrium position. Notice that's a spot where it has all kinetic energy and no potential energy. Essentially, for a pendulum, the thing you have to be careful of is just that we consider the equilibrium position, which basically is when the string is hanging straight down. We're basically saying wherever the pendulum bob is there when it's hanging straight down, that's the reference height for what we're going to call 0 height. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Moving on, I want to take a look at one more question here, conceptual question that I'd like you to take a moment to think about. It says a pendulum clock is moved from the Mississippi Delta region to the Rocky Mountains. Will the clock run faster or slower in the Rockies? Why? How can it be adjusted to compensate for this change? Describe your assumptions. I want you to at least focus on the first two parts of this question. A pendulum clock is basically like a grandfather clock, if you know what that is. Basically, because we're saying here that a pendulum is going to keep a constant period if it has a constant length, a pendulum clock can tick out 1 second if you adjust the length of the pendulum such that its period is going to be 1 second. If you move it from the Mississippi Delta region to the Rocky Mountains, why is the clock going to change in the first place? That's really the question you want to focus in on, and then take a look at, will the clock run faster or slower? Why? And how can it be adjusted? I want you to take a second to pause this video here and think about that. And when you think you've come up with an answer and reasons why, hit play and we'll go over it. Okay, so there are a number of things that we can say about this here, but I think the first thing that we should say, and I want to take this answer in pieces, is since the Rockies are at a higher elevation than the Mississippi Delta region, right? Mississippi Delta region is by the river, it's at sea level. The acceleration due to gravity is smaller at the Rocky Mountains. Right? The equation for the acceleration due to gravity is gm over r squared. The distance from the center of the Earth is larger because it's up at the top of the mountain. And so the acceleration due to gravity is smaller there. Now, of course, the question is, well, how is that going to affect the period of the pendulum? Well, since the period of a pendulum is inversely proportional to the square root of g, the acceleration due to gravity, according to the period of a pendulum equation, period equals 2 pi square root L over g, since g gets smaller, the period of the pendulum increases. Now, this is the part where you have to be careful. This means the clock runs slow because when it's supposed to have completed one cycle or one period, it hasn't yet. So it's behind. Think about it. If we have a clock that is basically saying when the pendulum swings back and forth, that's 1 second, and now it's taking longer than 1 second, the clock thinks 1 second has happened in an amount of time that's actually longer than 1 second. Like, let's say it actually takes 1.2 seconds. If the clock just thinks that's 1 second, but 1.2 seconds have actually passed, it's behind. It's running slow. That's the first part. Now the question is said, well, how are we going to compensate for this? Well, to compensate for this, we want to make the period 1 second again. And so to compensate for this change, you have to make the pendulum decrease its period to the value in Mississippi. Since the equation, period of a pendulum equals 2 pi square root L over g, says the period of the pendulum is directly proportional to the square root of the length, we can decrease the period back to its original value by decreasing the length of the pendulum. And the factor we would decrease it by is the exact same factor the acceleration due to gravity increased by when we went from the Mississippi Delta to the mountains. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, because we're talking about acceleration due to gravity and how it's involved with a pendulum, I would like to just take a brief moment to talk about how we can use a pendulum to measure the acceleration due to gravity. So, as we've been saying for a while now, when it comes to experimental design, it's all about the equations. A pendulum is a wonderful tool to determine the acceleration due to gravity on the surface of the Earth. According to the period of a pendulum equation, period of a pendulum is equal to 2 pi times the square root of L over g, If we know the length of the pendulum string and its period, we can determine the acceleration due to gravity, right? The only other variable in there then is g. Solved for g, the equation becomes g equals 4 pi squared L over t squared over the period squared. And so if we measure the period for pendulums, which I don't think is the plural of pendulum, I think it's probably pendula, but of course, whatever, who cares? If you measure the period with different lengths, so changing the length is going to give you a different period, so you'll get a bunch of different data points, we can get enough data to determine the acceleration due to gravity. The equation tells you everything you need to do. You need to change the length, and by changing the length, this will change the period, and then you're in business. You just collect your different data points. Take a second to pause this video here and write that down, and when you hit play, we'll move on. So just to be totally clear about it, you don't need to write this down again. I just had that as the last bullet on the previous slide. I'm just putting it here for continuity. Experimental theory says if the actual physics equation says g equals 4 pi squared L over the period squared, if I graph 4 pi squared L versus the square of the period, then I should get a straight line on the graph. And that straight line should have a slope that is equal to g. Now, a couple of years ago, I finally convinced the administration of Aviation High School to buy us a bunch of lab equipment. They did, and shortly after the AP test one year, we got a huge delivery of supplies. And so I told my class, after the AP test, do you guys just want to do like fun labs and just like screw around with all this new equipment? And they said, yeah, sure. And so we did. Basically, I said, I want us to do an experiment to see if we could actually measure the acceleration due to gravity with a pendulum. And so you'll notice here there's like just a stupid amount of data because I had 6 lab groups going at once. But I told them all just randomly pick a length and measure the period. Of course, you do this by having the pendulum swing back and forth 10 times and then dividing that number by 10, the time you get by 10. And so I told them once they collected a few data points, read out your data, tell me what the period was, and I'll type it into Excel, and we'll see what we can get. So notice here I have all these different lengths, these just randomly picked values that the kids picked, and the periods that they gave me. So I took the square of the period. That's going to be in my denominator. I took 4 times pi squared times the length that they told me. And I have now, notice, this data goes from column, or I should say row 2, all the way down to row, whatever, you can see. It's a lot of data. And look at that. When I graphed the information that we needed to graph, 4 pi squared L over the period of the pendulum squared, we got a broadly straight trend. Now notice, there's a lot of spread here. There's a good reason for that I'll explain in a minute. But notice the slope of the line on that graph is 9.98 meters per second squared, which is pretty good considering how crude this experiment was. Notice this is a less than 2% error that we got in this experiment. Now, the reason why we ended up having such a crazy spread for all this data is because I wanted to do a bunch of different experiments with these guys this year. So I just said, we're doing this quick. Don't go nuts. Make your measurements. Give me the data. Let's do it now. You got 10 minutes. And so they rushed through it. If they took more trials and were a little more careful, they probably wouldn't be so much spread. Notice, though, either way, the fact that we have 62 entries on this graph means we got the points above the line to be canceled out by the points below the line, and our smooth average here that we have gives us a value for the acceleration due to gravity within 2%. And that's pretty cool. The pendulum, I think it's important to realize, is a great tool for determining the acceleration due to gravity. Keep in mind when it comes to the experimental design question on the test, the equation is key. All right, guys, last question for today. Simple harmonic motion packet, page 32, number 25. A simple pendulum has a period of 2.5 seconds on the Earth. An astronaut then takes it to the surface of the moon. What period does the astronaut measure there? That is your task. Obviously, because today is Friday, this problem is officially due on Monday. But with that, that is it for simple harmonic motion for a pendulum. That is it for the simple harmonic motion unit as a whole. That is it for AP Physics 1. Congratulations, guys, we did it. All of the new material is finished. Now we are going to gear into review mode. Obviously, on Monday, I am going to post a video with the answer to this question and probably with an answer to the free response question you were assigned over the weekend. So this is not the last video per se. I'm going to put up a lot of videos. If I give you an AP Classroom, I might go over it in the form of a video. But this is the last of the new material for the year. All right, everybody. Have a nice weekend.